In this video, we're going to look at a new class of problems, and they're called volume of revolution problems. They're questions where we take revolutions, and by revolution here, we do not mean a political statement, but the analog of the word revolve, where we spin things around. It's that kind of revolution. We'll start off with an example. If we consider the graph of y equals e to the negative x, that's an exponential decay curve, and then we talk about the region underneath that graph up to the point x equals 3. We talk about that entire region, but we don't want the area of that. We want the solid, or the volume of the solid, generated by spinning that region around the x-axis. What that's going to give us is this shape over here in 3D. Our question now is, how can we find the volume of this structure here, knowing only the formula for the boundary y equals e to the negative x and the starting and end points? Well, we're going to take the same approach we've taken in other examples already in this unit, which is slicing up this volume into simpler shapes and then building up the total volume by looking at the volume of the little shapes and using an integral to add them all up. To get started on that process, we have to ask ourselves, what is the shape of any cut that we make? And let's choose perpendicular here to the axis of rotation. So imagine cutting this way, or in this scenario here, here's the axis. What if we cut in a plane like this? What shape would we see? Think about that for a moment, and then we'll check in. Okay. It's easiest, I think, to see on this picture that we're going to see something round. We're going to see something, in fact, circular. Does that make sense? Well, it's not totally convincing here, but if you think about what the rotation that we're using to construct this shape does, it takes this point and spins it around in a circle because we're rotating. So we are going to see a circular shape when we look at the cross section, leading us to the answer A in this scenario here. What that means is, as we take slices perpendicular to the axis of rotation here, perpendicular to the x-axis, we slice vertically, we're going to see circles, 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 and then we can probably use that to find the volume of slices and then add up the volume of all the slices using an integral. Our next step will be to explicitly get the volume of a cut, or we'll often term it a slice. Let's see how that pans out. We're going to be taking slices at several points along the way here, so let's imagine these various slices. Just from the picture and from our analogies to earlier work, the width of this slice is going to be delta x. And what are we going to get as a configuration? Well, we're going to get a circle. And if we give it a little bit of width, we're going to end up with a disk, like so. Or a thin cylinder, thin, flattish cylinder. Well, that's perfect because we know how to find the volume of cylinders. We don't know how to find the volume of, going back a page, this shape here, but we know how to find the volume of elements of that shape. What's going to be important? Well, it's going to be the radius, and we're also going to need to know the thickness, delta x. That's going to lead us to the volume of a slice being simply pi r squared. That's the circle area. From that circle area, we add the third dimension going this way, and that's going to be delta x, or the thickness. So with those ingredients, we have in principle the volume of any slice. Of course, this r here changes. It's 1 at the slice at the bottom here, and it's some other number down here. But can we find out a formula for r? Well, absolutely. This distance here is r. But that distance is also the y value on the curve y equals e to the negative x. That's how we define this graph. And so this distance here from the axis up to the graph is a y-coordinate, and it's defined by the curve y equals e to the negative x. And that's exactly what we want as our radius. So we use that substitution for the boundary here, and we're going to get e to the negative x all squared times delta x. Taking a careful look at this to make sure it makes sense. If you select an x value like x equals 2 and built the circle here with the thickness delta x to make it a cylinder, you would find its radius by using e to the negative x. Once you have that radius, you would build the area of the circle multiplied by the thickness, and that gives you a volume. And that is the key ingredient. Writing down the integral for the total volume is simple after that step. Because all we do is we take that pi e to the negative x all squared, the delta x becomes a dx, and we add all those slices up from x equals, in this scenario here, the first slice is at x equals 0, and the last slice occurs at x equals 3, given the words in the problem. And this integral represents a total volume because we can look at the units here. This would be in square units. Let's just call it u squared. And the dx has dimensions to it. It is little thin slices, delta x wide. So we end up with cubic units by the time we're done. In these problems, the setup is often the most challenging. The actual evaluation of the integral is going back to the skills that we've learned before. Here's a copy of our integral from the last page, and from this we can simplify a little bit to start with. First, rewriting without the x equals, that is always implied or matches the variable that comes with our d or our delta. We have the pi that we can bring out front, and if you remember the power rules, if I have a nested power like this, that is the same as e to the negative x times 2. We can treat it as multiplying of the powers. We'll rewrite that one more time. That would be more commonly written as e to the negative 2x. And now we're ready to do our integration. When we integrate this, we're going to get the same exponential back, and then we're going to have a negative 2 that we have to handle. If we divide by negative 2, that'll give us the right antiderivative, and then we're going to evaluate that at 3 and 0. That's going to give us pi over negative 2 times e to the negative 2 times 3 minus e to the negative 2 times 0. Simplifying that a little bit, we get e to the negative 6 minus 1, and that we can use our calculator for. And we obtain a value of approximately 1.57 cubic units. And I'll emphasize again, looking at this shape, as a shape, there's no simple formula for the volume enclosed in this picture. There's just nothing out there that would exist. However, this idea of slicing up this complicated volume into simple shapes, these little thin cylinders, and then accumulating those over the entire shape, gives us an integral that we can evaluate and leads to a relatively simple calculation of the total volume. So this is a very powerful technique for breaking down complicated accumulation problems into something that we can express naturally using integrals.